Swayam Prabha. Digital India. Educated India.
Dear students, in this session we will discuss briefly the most widely used manufacturing processes. First, the metal casting, which is also called near net shape process. Metal casting is one of the oldest known methods for shaping materials. It involves pouring molten metal into a mold having the required shaped cavity. The cast, also called material filled inside the mold, is then allowed to solidify. Next, the metal object is taken out from the mold either by breaking it or taking the mold apart. The solidified object is called the casting. In this process, intricate parts can be given strength and rigidity, which is frequently not obtainable by any other manufacturing process. Major casting processes are sand casting, permanent mold casting, continuous casting, die casting, slush casting, centrifugal casting, evaporative pattern casting, lost wax casting, shell molding, vacuum sealed molding, etc. Molding. Molding is commonly used term in plastics, which is also a net shape process. A hollowed out block in which liquid, plastic, molten glass or ceramic material is filled is called a mold. The filled in material hardens and gets set inside the mold, replicating its shape. In order to remove the hardened substance, a release agent is also used. There are several molding processes. The major molding processes will be briefly introduced now. Hot compression molding, transfer molding, injection molding, extrusion molding, laminating, vacuum forming, expandable bead molding. Then comes to metal forming, which is also a net shape process. Metal forming is a process which involves shaping of materials in a solid form. It can be defined as a bulk deformation process that induces change in shape under the applied force. Classification of metal forming processes. Metal forming is basically grouped into two types, namely hot forming and cold forming. Hot forming is the process which is performed by heating the metal above its recrystallization temperature. The recrystallization temperature is the temperature at which new grains start forming, replacing the older grains. It is generally between 0.3 to 0.5 times the melting temperature of any material. Hot forming reduces the material's yield stress, so that its shape can be easily changed or formed by applying lesser forces. The rate deformation is higher in hot forming, and it is used to make billets, ingots, etc. Cold forming. Cold forming is performed by heating the metal below its recrystallization temperature. It requires higher mechanical forces, stronger equipment and tooling in order to withstand the larger applied forces. The mechanical properties such as strength, hardness, etc. increases after cold forming. The voids and vacancies get narrowed due to applied forces. The surface finish of the cold formed parts is usually better. The equipment and tooling costs in cold working are comparatively higher than hot forming. The major metal forming processes include smith forging. The example is goldsmithy and blacksmithy works, and the product example can be an axe. Drop forging, which is used to make hand tools like spanners. Next process is extrusion. It is a metal forming process of extruding the material from a shaped die. A finished product can be produced using this technique. The product examples include channels, bars, tubes, gears, etc. Drawing. Drawing is an operation in which the cross section of solid rods, wire or tubing is reduced to change in shape by pulling it through a die. Drawn rods are used for shafts, spindles, small pistons and as the raw material for fasteners such as rivets, bolts and screws. Drawing also improves strength and hardness. When these properties are to be developed, by cold work and not by subsequent heat treatment. In this process, a set of die is placed through which the material to be drawn or pulled through by applying certain force. This reduces the dimension of the input material and a weir or rod of different dimension is produced. This die angle forms a critical parameter in this process. Sheet forming. Sheet forming in general can be done by hot or cold working. Desks, file cabinets, car bodies, beverage cans, etc. are some examples of sheet formed products. For aerospace applications, the common sheet materials are aluminum and titanium. Major sheet forming processes. First, roll forming. This process is used for forming continuous lengths of sheet metal and for large production runs. The metal strip is bent in stages by passing it through a series of rolls. The parts are then usually sheared and stacked continuously. Stretch forming. In this process, the sheet is clamped along its edges and then stretched over a die or form block, which moves upward, downward or sideways depending on the particular machine. Stretch forming is used primarily to make aircraft wing skin panels, automobile door panels and window frames. Next process is spinning. This operation, which resembles forming, can be carried out on a machine such as lathe. It could be achieved using a suitable tool or by using a mandrel. Electroforming. In this process, electrical energy is used to execute large scale forming such as hydroforming. Explosive forming. In explosive forming, controlled explosive reactions enable the forming in sheet metals and other metallic products where the rate of deformation is high. Press working. Press working is a chipless manufacturing process by which various components are made from sheet metals. It is also called cold stamping process. Press is a machine in which there are two or more slides which move relatively to compress the material in the desired shape. Different types of presses are used for various applications such as paper trimming, wood ply or woodworking, sheet metal cutting, bending, deep drawing, etc. Then different types of presses are classified based on source of power. For example, mechanical, electrical, hydraulic, pneumatic, etc. Then can be also classified based on method of slide actuation. For example, crankshaft, eccentric, cam type or rack and pinion type. Presses can also be classified based on number of slides. For example, single, double, multiple. Then presses are also classified based on type of frame. For example, solid frame, C frame, movable frame, tie rod, etc. They are also classified based on the purpose and end uses. Then press working products, blanking. Blanking is an operation in which the blank obtained is the desired product. The rest portion is discarded. Here, as shown in the figure, the useful part of this entire sheet is the blank produced. In contrast, in piercing process, the sheet with the hole is considered as the useful product. The corresponding metallic part produced as a result of producing this hole is now discarded. Thus, the sheet with the pierced hole becomes the useful part. Example for this process is a washer is made by blanking and punching or by the combination of the processes at a time. Perforating. A sheet with a patterned multiple holes made in a single press stroke is as shown. The sheet is perforated in a particular pattern. Next process is embossing. It is a process for making impressions, for example, coins or embossed sheets. Bending. This process is used for making bends in sheet metal, rods, channels, etc. as per the requirement on a press. Notching. Notches are made as required, basically in a sheet metal. So, here this is the sheet metal in which notches of the desired dimension are made, Another process is nibbling. A designed profile, for example, a shaving blade's internal profile is made using this process. This profile is tiny, at the same time bit complex. This is the process which is most suitable to carry out this manufacturing. Cup drawing. This operation is done on a press. A round sheet metal blank is placed over a circular die opening and held in place with a blank holder. The punch travels downward and it forces the blank into the die cavity, forming a cup. Depending on the diameter to length ratio, the operation is categorized as shallow drawing when the L by D ratio is less than 1, or deep drawing in which length to diameter ratio is greater than 1, where L is the length and D is the diameter of the draw. Let us move on to material removal processes, also known as subtractive processes, or we call as machining processes. Material removal or machining processes are called subtractive processes. In this process, the excess material is removed to give the final shape to the product and are often termed as secondary or machining processes. The processes which are used to obtain the required finish or tolerance to the end product are also termed as finishing processes. This means that in both the cases, that is either removal of material or finishing of part, the product to be cut or finished is made by some other processes described earlier. At instances, if the product geometry is very complex, a combination of different processes are used to make the final part. Some examples of metal removal or machining processes are milling, turning, drilling, broaching, shaping, planing, honing, etching, grinding, abrasive flow machining, abrasive jet machining, water jet machining, electron beam machining, laser beam machining, etc. Let us move on to joining processes, which are also called additive processes. There are three basic methods of joining material together. Number 1, using fasteners like rivets, screws, bolts and nuts, etc. Number 2, adding low temperature bonding material in between, like in brazing and soldering. And number 3, fusing the material together. These have properties similar to the base metal and considered as permanent joints. Welding. Out of the above three categories, the most popular method is welding, in which materials are joined permanently. Welding is defined as the process of joining two similar or dissimilar metallic or material components through the application of heat. In welding, filler material can be used and pressure may be applied as per the necessity. Different types of welding include arc welding, submerged arc welding, gas welding, thermite welding, plasma arc welding, plasma MIG welding, resistance welding, etc. Other welding methods are solid state welding, ultrasonic welding, explosive welding, friction welding, electron beam welding, laser beam welding, etc. Let us move on to rapid manufacturing, which is also additive process. Rapid manufacturing is an emerging additive fabrication technique. It is used in manufacturing mainly for making solid objects. It uses an additive approach by sequential delivery of energy and or materials layer by layer. The rapid manufacturing machines fabricate plastic, wood, ceramics and metal powders to form physical objects. In order to control the process, computerized programs through mathematical modeling are made. Rapid prototyping processes. In rapid prototyping, fabrication of a physical three-dimensional part of any arbitrary shape is carried out directly from a CAD database by a quick, highly automated and totally flexible process. This is a relatively new material additive manufacturing process in which a part is produced by depositing layers or by joining particles of raw materials. Examples of rapid prototyping processes include stereolithography, selective laser sintering, fuse deposition modeling, three-dimensional printing, laminated object manufacturing, laser engineered net shaping, etc. The manufacturing processes can also be classified in the following manner, that is based on energy used. Based on energy use, the processes can be divided like conventional processes and non-conventional processes. In these conventional processes, mechanical and electrical energy are used for the processing. However, in the non-conventional processes, the energy from chemical, ultrasonic electrical discharge, laser, etc. are used. So, this can be like categorized something like this. Another classification of manufacturing processes. So, this is conventional and this is non-conventional. So, this is based on, we can say, energy used. Now, in this conventional, basically the energy form of energy used is mechanical and electrical, which are most common in almost all processing, material processing techniques. However, in these the non-conventional methods, so here something like chemical energy or the chemical processes, or it can be ultrasonics, or it can be discharge energy like is used in EDM, etc., or it can be nuclear energy, or it can be like laser energy, etc. That means the processes, say for example, nowadays the laser machining is very popular. So, laser machining, so for making, to make small holes, small diameter holes, this laser beam machining or also called LBM, laser beam machining, is very frequently used. So, this falls under the category of this, which is not a very conventional mode of energy. This requires a special device. We use electrical energy, no doubt, for these processes, but not as it is. We use electrical energy to produce laser, and this laser is directly used now for material processing. That means, the work done is through laser heating, not by the conventional electrical energy. So, this is the difference between this conventional mechanical or electrical form of energy use or the non-conventional energy use. Then another classification could be based on the size of products. So, this is relatively a new approach in which we can group products by their size, which are manufactured in the domain of macro processing, micro processing or nano processing. So, generally this also can be, let us see in this way, by, so manufacturing processes, again manufacturing processes. So, this can be as say macro, then micro and then nano. So, this is based on size of products being manufactured. Now, the most of the products we see or we use in general are in the macro domain, but micro domains, there are certain products like powder, most of the powder materials. So, these and nowadays even the electronic components, so those are manufactured in micro domain, like say for example, the components needed for IC or integrated circuits or most of the electronic gadgets, they use components which are very small and in the micro level. So, these are also being produced. Now, if someone says where is the exact demarcation line between this macro and the micro, it is not very clear cut, but from our experience we can generally say the micro is in the domain or where the size is in and around 1 micron, or some researchers say that if the machining produces the chip which is produced which is in the size of 1 micron, so that can be called as micro machining. So, is the case with which is the micro component. So, a clear cut definition is yet to be evolved. However, like MEMS, micro electromechanical systems, so there are number of components, mechanical components are also there, say gears may be there, some channels may be there. So, the sizes of these may not be very clearly defined, but in a relatively very small domain which we can comfortably call as micro domain. So, is the case with this nano. Generally in the nano scale, the sizes or the size or the components or the products that fall in the nano category or nano size, nano scale can be considered as the nano domain. But again, to arrive at a particular number that defines micro and nano as a product or micro manufacturing and nano manufacturing as a domain is practically difficult. However, the concept is the approach that is needed for macro manufacturing, micro manufacturing and nano manufacturing may differ substantially. The same equipment, same machine may not used very widely for macro products to be produced, may not be useful for micro products to be produced. Similarly, they may quite different, they may be quite different for producing the nano products. So, therefore, it is always better to define these domains as a different manufacturing domains, like the precision we need for micro machining, the tools we need for micro machining are substantially different from those used in macro machining. So, is the case with nano manufacturing, in which even the environment can be or should be controlled apart from the machines different, tools different and so on. That means, the total approach is different significantly from that of macro and micro domains. The macro processing involves machined features in the scale of millimeters and more. In micro processing, the features are less than 1 millimeter generally. As I have already indicated, some researchers say any process that produces chips of less than 1 millimeter can be termed as micro machining. Examples of microprocessing are micro freezers on turbine blades, micro reactors, micro channels for microfluidics, micro holes on needles for medical applications, lab on chip, then heat exchangers, micro channels for heat exchangers, and so on. In nano manufacturing, on the other hand, the size of chips and the surface finish produced are in the range of nanometers. Therefore, as the chip size we can say is in the nanometers, therefore, the techniques to be used also accordingly should be suitable. That means, it will be in terms of few atoms. Examples of such products are engine blocks and cylinders, wherein the internal finish required is very high. As the scale of processing features reduces, the time and cost required increases. It requires special skills as well as special technology to produce nano features on products. As I have already indicated, as we go on nano level, even a dust particle which may have several micron diameter can affect the entire manufacturing itself. Therefore, the environment control in nano manufacturing is also an important aspect. We have to have special environment. Then the surface produced or the machining, generally machining is a production of new surface at a nano level may get immediately oxidized and form a different substance. Say for example, if it is oxidized, then instead of a metal, the surface will become metal oxide. Then removing down metal oxide instead of metal may require a different amount of force and accordingly a different equipment as a whole. Therefore, the control of the environment is also an important aspect in case of nano manufacturing. Thus, what we understand from this discussion is macro, micro and nano manufacturing that needs different conditions, right from the machine tools used, the cutting tools used and the environment used. So, therefore, we have some logic to differentiate them or categorize them in three different categories like macro, micro and nano manufacturing. Making the tooling for micro and nano manufacturing is extremely difficult and challenging. This is what I was telling. Say for example, processes like wear electric discharge grinding are used for producing such micro features on extremely hard metallic tools. Thus, for nano manufacturing, again the production of tool itself is a big issue. Therefore, it is logical to separate them out, which may require, say for example, chemical processing for making the tool itself, whereas in most of the macro manufacturing cases we go for mechanical processing of the or shaping of the tool, or we can say form tools etc. for the macro level manufacturing. In the end, let us summarize what we have discussed in this session. In this session we have discussed about different categorization of manufacturing processes, different approaches towards categorization we have seen based on different aspects, based on energy used and based on the size of the products and so on. We hope the session was informative and interesting. Thank you.